Awesome, cool. Well, thanks everyone for sticking around. My name is Patrick. I'm an experimental psychologist and I study human multi-agent coordination. The talk I'll give is presenting some work using DRL led by my office mate, Gaurav, who couldn't be here due to visa reasons. So I made the long trek to be with you here today. And so to start, there we go, cool. So yeah, so working within teams, within shared physical or virtual environments, I do a lot of virtual reality, social virtual reality work as well, requires the coordination of attention and selection and timing of actions by each individual agent in order for them all to contribute meaningfully towards a shared goal. And of course, working together as a collective over just working by yourself has the obvious benefit of being able to solve tasks quicker. But not only that, working as a team kind of affords the discovery and exploitation of novel strategies that are just not obtainable to individuals alone. And so a really clear example of that is the formation of a bucket brigade, where by definition you need other people in order to efficiently transport these objects. And success in teams is not guaranteed. Otherwise, every competitive sports game would end in a tie. So there's a lot of variation in terms of the types of strategies that teams adopt, or just how effective they are in executing those strategies. And my interest in AI generally is, we do a lot of work on developing models, replacing human agents within these human teams. But not only that, I really have an interest and would love to find collaborators on just how can we intelligently use these agents to steer interactions to help teams discover these more optimal strategies. As you may know, in DRL, self-play is used a lot in training these RL agents. And they're really great, these competitive tasks such as Go and Dota. But what was shown in work by Carol, for example, is that this typical way of training agents does not transfer well, or it's at least not guaranteed to enable fluid human AI coordination. So in this case, the self-play agent trained with another self-play agent is working with the green hat, which is a human player. And you get these situations where you're kind of just bumping into each other and it leads to not as fluid of an interaction when it comes to serving onion soup. And so their solution was, okay, well, if you endow the training environment with an agent that exhibits kind of human models for pre-recorded data, and then have these self-play agents interact with the human model. Indeed, when you do that kind of approach, it leads to policies that leads to more effective human AI collaboration. But what if you don't have access to this human data? Let's say you just never did this pre-data collection, or you just don't have sufficient amounts of data. An approach we use in our lab, in conjunction with behavioral cloning type approaches, is you can exploit the fact that in perceptual motor tasks generally, complex human movements can be decomposed into what are called motor primitives, where complex actions could be represented as either being discrete or rhythmic. So discrete actions are reaching for an object, throwing a ball, where there's a definite end state. And then rhythmic behaviors are, waving your hand, walking, speaking, has a rhythmicity to it. And conveniently for modeling, you can represent these dynamical primitives using low dimensional dynamical systems, such that discrete behaviors can be modeled using fixed point attractors, and rhythmic behaviors can be represented using limit cycle dynamics, like a nonlinear oscillator, for example. So what we do in our lab is we compose models kind of consisting of these dynamical primitives to design agents that could interact with humans. And we use VR. Basically, we don't have our own robots, so we just do everything virtual reality. And so we do things such as developing models and comparing, for example, individual trajectories compared to DRL agents, cooperative pick and place tasks and passing decisions, competitive tasks such as air hockey, so looking at the postures of kind of attack versus defense. And then kind of also moving away from these dyadic situations, also considering larger team structures. So in this case, this is a 4-person search and rescue kind of task. But the bread and butter task that we often use, and I think what really clearly demonstrates the utility of the dynamical motor primitives is what we call the shepherding task. And I propose that this is a great baseline environment to use in DRL, in addition to Hanabi and Overcooked and stuff. So hopefully I can convince you of that. And so in this task, we have participants come into the lab and they play on this kind of table screen here, and they have these handheld controllers, and these handheld controllers control their respective dog or shepherd, which are these 2 squares right here. And what participants have to do is that they have to work together to find some sort of strategy to corral and contain a set of evasive autonomous agents, which are these little balls, which we call sheep. And their job is to keep them contained within that red circle for a certain amount of time. There are two primary modes of behavior that we see participants adopt while doing this task. The first of which is something we call search and recover, where here, very early on, participants will intuitively subdivide the task space in half. There's a my side, your side, and each player will go to the target that's farthest from the center and move it towards the goal location. This strategy is relatively effective if the number of agents you have to corral is relatively low, it's like 3, for example, or if the agents are really slow moving. But as task difficulty increases, this is not a useful strategy and it leads to task failure. So participants, I do have to note also for this task, this is a non-verbal, no verbal communications allowed, so people have to kind of non-verbally negotiate how they should go about solving this task. That's pretty much due for just the simplicity of our analyses. And so over a 45-minute session, some participants just fail and cannot solve this task. But for those who do solve it within this 45-minute period, we see the spontaneous emergence of a different mode of behavior, which we call coupled oscillatory containment. Where here, instead of worrying about each individual agent, participants suddenly discover that, hey, what we should do is just form a wall around this herd, and that does a really good job keeping them contained. And when we ask participants afterwards, kind of like how do they come about using this strategy, the type of language they use really does kind of seem to suggest that it's a moment of cognitive insight, kind of reorganizing how they actually perceive the problem itself. And indeed, once you discover this strategy, kind of leads to ceiling levels of performance. And so what we did, in terms of the modeling front, we kind of been using these kind of like heuristic-based models where we took, taking this behavior, we decomposed it to different problems. We have the target selection problem and the action dynamics, how you move about this environments. For target selection, we just employ a heuristic-based rule. So select the target that's farthest from the center, that's closer to me than my partner. So we kind of bake in that coordination within the heuristic rule. And for action dynamics, basically, just in summary, we modeled the behaviors that we observed in human participants using these dynamical motor primitives that I mentioned before. And the model is capable of exhibiting both the search and recover and oscillatory containment, as well as flexibly switch between these two behaviors. In a kind of human-machine interaction task context, we've validated our model with novice participants. So this is, kind of, you see like a little two-dimensional game screen here, but this is kind of embedded within a virtual reality task where we have participants come into the lab, they put on a VR headset, and they're actually interacting with another avatar completing this task. And we tell them they're interacting with another human participants. And so we kind of do like a little Turing-like test. And so in this case, our agent's this blue one on the left. It's kind of hard to see, but it's the top one on the right there. And so the agent's able to work with participants and solve the task, either in our original configuration, just keeping the red circle. And here it's a little bit, there's fewer constraints where you just have to keep them together just in general anywhere. And during debriefing, when asking participants, to the extent to which they believe there was a human partner they're interacting with, most still remain in belief that the avatar was human generated, that there was another participant in another room, which provides some evidence that not only does our model, is our model able to kind of solve the task with participants, but that it's able to kind of capture essences of human coordinated behavior in these kind of perceptual motor tasks, in a specific perceptual motor task context. So we have this kind of heuristic-based model with this target selection rule and a model consisting of dynamical motor primitives. And the problem with heuristic-based models, of course, is that it's kind of, we engineered it. A lot of effort went into kind of parameterizing it. And so we're really interested in to the extent to which we could extend our models to develop agents with potentially better and more flexible policies. And so the way we go about doing it is that we kind of treated these two components as two separate things that we could train. So you could do something where we replace the action dynamics with a neural network, train that using DRL. Or we use these dynamical motor primitives, make that the movement constraints for the agent, and then have it select which targets they should select while doing this task. I also tried like a completely black box approach where we had two separate neural networks doing both target selection and action dynamics. However, we just cannot train it. No matter what kind of curriculum we gave it, what kind of reward shaping, we found it super difficult. So maybe for those who have strong computational DRL backgrounds, you can help us out there. But yeah, just to summarize the training, we implemented this curriculum where it's this 11-step process where we slowly increase the number of agents that had to be corralled, as well as increase their speed slowly. And the reward structure was just that we gave them positive feedback if all the targets were within the red circle, negative if they were too far away. And then we also provided a small negative feedback if they were too close to each other, just to kind of promote this division of labor type strategy. And so these are just some just a summary of the training results. So on the x-axis is just the curriculum steps, and then this is the cumulative training steps needed. And probably unsurprisingly, so when we constrained the agents to use our dynamical primitives, and it just had to train which targets it should select, it was able to go through a curriculum in the fastest amount of time, followed by the agent that had to discover its own action dynamics policy. And like I said, we couldn't really train a black box agent, but what we did is that we provided information directly about which targets to select. So we basically mimicked this policy here. And then at some point during the curriculum learning, we then allowed it to develop its own target selection policy. And then you can see that it takes longer to get through the curriculum, which may not be surprising, right? Because we basically are reducing the dimensionality of the training problem. But what was more important for us is kind of testing to see the extent to which these agents are able to actually collaborate with humans in this kind of shepherding task that we have. And the way we did that is we use this kind of training and transfer task-like approach, where we'll have participants come into the lab and they'll have to play with one of our agents that we developed, either a heuristic-based agent or one that is either trained using with a neural network. And then after training, we'll do this transfer task where similarly trained individuals come together and do a modified version of the task that they haven't seen before that has kind of a new objective. And just to summarize what we did, these are just results from this paper here. So for this paper, we only did the comparison between our heuristic-based model and a model where it had to develop its own action dynamics policy. So here we're basically fixing the perception side and then really comparing the action dynamics side. And what we find is that during training, participants are able to complete the training at higher levels of performance with the artificial agent and exhibit more oscillatory behaviors. During the transfer task, that level of skill persists with the new partner compared to this model here. And then we also have a separate sample where we had participants interact with our various agents, and they preferred working with this heuristic-based model as opposed to the one where the action model was trained using DRL. Of course, the critical step is this other option here, which we're in the active data collection for. So I don't have those results for you, but hopefully in a couple months, we'll have that as well. So kind of to summarize the findings is that basically our agents who are constrained using these dynamical motor primitive models are able to collaborate with humans in this task context and are the preferred models compared to an agent whose action policy was trained using DRL. And just a preview of some of our future work. We're kind of now looking into like the perceptual side. So looking at kind of these policies that are these networks that are trained to do target selection. There's a student, recently graduated student named Fabrizia, using explainable AI techniques to kind of differentiate novices versus experts, as well as the decision-making behaviors of these different policies, to see kind of what are the input features that are most important that differentiates those who discover these strategies versus those who don't. But just to conclude, as I only was given 10 to 15 minutes, is that despite the potential complexity in human behavior, the goal-directed behavior generally is very low dimensional in nature and shows kind of dynamic similitude across contexts. And then kind of to summarize that point, basically, as agents interact with their environment, there's these dynamics that are generated based on their interaction, which could be summarized using what are called behavioral dynamic models or task dynamic models, which you could formalize as dynamical systems, which are what these dynamical motor primitives are composed of. And then once these dynamics are generated, right, you could have this kind of top-down process that kind of constrains, kind of like this realization process where you kind of realize these dynamics and then an agent could then exploit them explicitly. And these types of dynamical models translate to different environments. So I've only talked about this tabletop task, but we also did some other work where we actually had people navigate a virtual environment through locomotion to solve this task. And even though in this case the behaviors look different, they're both predictive from the same dynamical model. And I love like BBC documentaries. And so, right, there's a lot of similitude with what we see in other animal systems. So I just want to give a shout out to Garv. He's the one who did all the DRL work. I did the original shepherding work. Lily's done the human AI preference comparison study. And then I mentioned Fabrizia, who recently got her PhD, is doing the explainable AI stuff as well. So thank you so much. Yeah, I'll take any questions you may have.
Thank you, Patrick.
Yep.
That was amazing. Any question? Yes.
Hi, thanks for that talk. It was really interesting.
Yeah, I'm just gonna get some water while you ask. Yep.
First off, I think I might beat you in terms of travel distance. I had to travel 2 hours from Adelaide to Sydney and then come here.
So you're my Adelaide person. Okay.
Yeah.
Cool. Okay. Awesome. Awesome. Okay. Yeah. I was wondering where you were. Okay. Cool. Darn. Okay. I got second place then. Okay.
I was wondering in the cases in the DRL in the deep reinforcement learning where the humans weren't preferring to play with the reinforcement learning agent. I was wondering, is that because the reinforcement learning agent was forming social conventions that the humans weren't able to interact with well?
So
I just trying to get some insight into why you might think the humans didn't prefer the reinforcement learning agent.
Yeah, so good thing I have some backup slides just in case. I think maybe I could do this one. This one's based in these are gonna be so hard to see. But you know, it's kind of like obvious stuff. Okay, so you can maybe see there's this little cyan dot right here. I believe that one is that model. It's, you know, it's typical behaviors, right? Is that the movement behaviors are very jittery, for example. And so it's able to, granted, this is interacting with one of our heuristic models. It's just, I think it's the level of noise. I actually haven't interrogated the videos so much compared to Gaurav, who, like I said, was leading this project. But that's the general idea, is that our heuristic-based model, So heuristic-based model in this particular study, so usually we have like a social coupling term so that the behaviors of the agent is directly coupled to those of the partner. In this case, we didn't include that coupling term to make it more comparable, I believe. I think you could quote me on that. I'm like blanking now. But yeah, further investigation, we'll kind of have to see exactly what aspects of the behavior, but just from visual inspection of these videos, it's just kind of like one of those obvious things where it's like, you know, the policies it's developing, because remember, this is a continuous control problem as well. You know, it's kind of jitter, adding more jitter and stuff like that. Does that answer a little bit of your question? Otherwise, I could forward you to Gaurav, who would be able to tell you everything about that. Yeah.
Yeah, cheers. I might grab his details after this.
Yeah, for sure. Yeah,
cheers.
Exactly.
Thank you.
Yeah.
Thank you.
Yeah.
Hi. Thanks for the talk. I really enjoyed it.
Oh, thanks.
For the task that you proposed, is the kind of wall policy, like the policy where they just kind of form a wall on the top and bottom?
Yes.
Is that like the single optimal policy that exists? Because in that case, you know, you can just have your agents play in self-play, and that would really only be, I mean, like that would be like the only convention that you really need.
Yeah, right. So I'll just play like these videos too, just as an example in the background. This is about something different. This is kind of showing how these behaviors are emergent kind of for free using, you know, kind of taking like a self-organization kind of story. And what we see is that it is based on kind of the constraints acting upon human systems. So because they're interacting at a tabletop, they can only reach so far, for example. The best type of policy as a human user you can adopt is something like this. And right, you have to remember, like, assuming this was human participants in this example, you have physical embodied arms, right? And so you can't, like, for example, move around in a circle effectively because you bump into each other. And so, so in a two-person case on the tabletop, you see something like this. In full body locomotion, what you see instead is that people kind of spin around the entire herd because they don't have that constraint of the arms, for example. In a single player case, this is what our transfer task was, you can just adopt this kind of circular-like behavior. So right, the key is like forming a circle of some sort, right? However, that kind of circle idea isn't a obvious solution to most participants at the very beginning, and that's something that needs to be discovered. But through this simulation work, it does seem to suggest, depending on the constraints acting on the animal and the type of environment it's in, you do see kind of differences in how the policy is unfolding, but it could be explained by the same dynamical model. Yeah. hopefully that answers your question.
Thanks.
Yeah, thank you.
You kind of answered my question on that one, because I was going to say, like, I don't know if I misheard you, but it sounded like the agents had some sort of penalty for getting close to each other.
Yeah.
So I was thinking this whole like oscillation behavior, I was intrigued why an agent would learn that and not go in a circle. But the fact that this is played on a tabletop.
So yes, exactly.
So do they, in this case, do the learning agents play a sort of best response to whatever the human behavior is?
It is, so what's given as in, so you're saying the agents trained using DRL or heuristic based? Oh yeah. So the inputs for that, so it'll receive just the states of the environment, and it'll just select whatever action, and it just does that. It can select whatever target it wants. So yeah, it doesn't like infer. I mean, with the penalty, hopefully it's inferring that if my partner is pursuing this target, I shouldn't pursue that one. But that's not guaranteed. Yeah.
Okay. So like, but the human starts playing, and then the RL agent is just kind of acting in conjunction with wherever the human is.
Yeah. So it's updating. Yeah. So
So did the human discover that kind of half moon oscillating policy?
Oh yeah. So there'll be some. So yeah. So what we see is that with the DRL agents, you do see that behavior emerge, not at the same level compared to our heuristic-based model. So it is possible, but yeah, not at levels that we see when participants would work with another human or with our heuristic-based model. But yeah.
Okay, cool.
Yep.
Thanks.
Yep.